Okay, so I want to talk about how I can translate a linear transformation into something that can be written with a standard matrix. So we saw in the proof of this previous theorem that if I have a transformation T from Rn to Rm is linear, then T of x is equal to Ax for some matrix A. And in fact, we saw that A is actually equal to transformation of what happens to the basis vectors. So these are going to be the columns of A. And so what I want to do here is I want to look at an example that is not given as a matrix, but as something else. And then I want to translate it to a matrix in this form. So, example, suppose T is the transformation from R2 to R2 that rotates each point, let's say in a plane, so we're in R2, and I'm going to say it rotates each point theta degrees counterclockwise. And I want to find the standard matrix for this transformation. All right, and if you'd like, pause the video here and see if you can at least draw a picture to sort of visualize what's going on. And then we'll come back and see if we can do that together. Okay, so let me draw a plane first of all. So here, this is R2. I can kind of think of this as my x-axis and this as my y-axis. And let's say I have some point, maybe a point here. We connect it to the origin. This transformation is going to rotate this counterclockwise. So that would be here, theta degrees. So maybe that moves it over here. So if this is, maybe I'll call it U, this would be T of U. Okay, so what this up here tells me, so if I want to find the standard matrix, it tells me that I am going to use this definition. And since I only have R2 to R2, I'm actually just using this part. And all that means is that I need to find out what happens when I transform E1 and when I transform E2. So let me encourage you also to pause the video and see if you can draw E1 and E2 on your picture and then see what would actually happen to them. Okay, so let me do that. Let me use blue to represent the point E1. So E1 I can think of as, so let's see, E1 in this instance is equal to 1, 0, since we're in R2, and I can think of this as the point 1, 0. So let me put that here. So 1, 0. And then if I have E2, I can think of that as 0, 1. So let me draw that here. Be 0, 1. And if I take this transformation, then I am moving, and let me also actually draw, let's put these on a circle, the unit circle, right? And if I take my transformation and apply it to this point 1, 0, I am going to move it theta degrees counterclockwise on here. And so what I'm interested in is what this point would be. And so it turns out I am still going to be distance 1 away, but another way to write this is as cosine of theta times sine theta. Sorry, cosine of theta comma sine theta. Okay, and that just goes or comes from the unit circle, and I'll say that actually knowing that is not necessary for this class, but what I want you to see is that this is something that is defined in this very strange way, and I'm going to be able to create a matrix to represent it. And so similarly, if I'm looking at E2 or this point 0, 1, then my transformation is going to rotate this theta degrees counterclockwise. And a way to represent this point here is negative sine times theta and cosine theta. And sorry, I shouldn't be saying times theta. It's sine of theta and cosine of theta. And so here I can see that this is negative sine theta. This is cosine theta. And this one we said was cosine theta sine theta. And what this tells me is that A is then equal to, the first column is what happens to E1. So cosine of theta sine of theta. And here again, you'd be given theta, it'd be something like 45 degrees, and then you would have an actual value here, cosine of 45 degrees or whatever it is. And so here I would have negative sine theta, cosine of theta, and this would be my standard matrix. Standard matrix associated with